All right, let's get this party started. Good morning, good afternoon. We're doing Unit 5, Lesson 9 today, linear models. Let's model situations with linear functions. It's been a while since we've talked about that word, but linear means straight line. So we'll focus on that when we get to it, but let's get it. The warm-up started, 9.1 candlelight. A candle is burning. It starts out 12 inches long. After 1 hour, it's 10 inches long, so it sounds like it's going down 2 inches per hour. After 3 hours, it's 5.5 inches long. When do you think the candle will burn out completely? Well, that ruined my prediction, because if it's 2 inches per hour after 3 hours, it should be 6, which would mean left, but we're at 5.5, but we can go roughly after that. So after 3 hours, it's halfway. So after somewhere between 5 and 6 hours, maybe. But it just says, when do you think? So that's when we'll think, somewhere around there. Is the height a function of time? Does the height depend on the time? Every time I give it a height, do I have a time? Or better yet, every time I give it a time, is there a height? Is there only one height? Yes. So is it a function of time? Yes it is. Does the height depend on the time? If I were to graph this, this would be height, and that would be time. For every single time, the height would go down and down. For every single time, I'd only get one height. So yes. If yes, is it a linear function? Explain your thinking. So it's been a while since, like I just mentioned, since we've talked about what linear means. But linear technically means we want a straight line. Now, just because it's not straight doesn't mean it's not data information that we can't use or that's not worthwhile, but linear technically means it's a straight line. And as if you didn't hear me just say, if it was at 12 inches and then it's 10 inches after 1 hour, that means it went down 2 inches in 1 hour, which means after 3 hours, it should be going down 6 inches. But that means that should be 6, but that's 5.5. So is it linear? No, because this isn't actually going down constantly. It could be, think about a candle melting. It's not going to melt exactly the exact same amount every single hour for whatever reason. Every once in a while, if you ever look at a candle, a big blob will just finally go and it just goes down slightly faster. So yes, it's a function because for every input of time, I only get one height out of it. However, it's not linear because it's not going to be straight. It's not going to give me an exact amount every single hour. And that's fine. It just means it's not linear. So here we go. 9.2, shadows. When the sun was directly overhead, the stick had no shadow. I don't know if you can tell, but there's a stick right here. Here's the stick. Here's the stick. And here, there's no shadow here. There's a little shadow here, a longer shadow there. So when the sun was directly overhead, notice on the picture on the left, there's no shadow. After 20 minutes, the shadow was 10.5. So it's 10.5 centimeters long. After 60 minutes, it was 26 centimeters long. Based on this information, how long is it going to be after 95 minutes? Well, we could guess this many different ways. After 60 minutes, it was 26. So one way to look at this is, let's say, if it was 26 after 60, add another 20, which was 10.5. So I'm just going to write some of this down. You could do this any which way you want. And again, I should have prefaced this video with this. Pause this video at any point if you want to think some of this through on your own, and then compare your thinking to mine. That's always the best way to do it. But with that being said, after 20 minutes, it was 10.5. After 60 minutes, it was 26. So if I did this plus this, that'd be 80 minutes. So that would be that plus that. And that's 36.5. This is the way I'm doing it. You could actually try to figure out many other ways, but that's not quite 95, and it just says estimate. So if I did 100, that's doing 20 plus 80. So I'm going to do 10.5 plus 36.5. So that's going to be 47. So after 95 minutes, it's going to be slightly less than 47. How about 45 centimeters? That's our guess. And maybe your guess was 40, or maybe it was 50. Doesn't matter. Hopefully it's somewhere right there. It does matter a little bit that you're not that far off, but there's lots of different ways to go ahead and predict this. But that's my prediction. Number 2 says after 95 minutes, the shadow measured 38.5. How does this compare to your estimate? Mine was a little more. That's how mine. Maybe yours was a little less. I don't know. But mine, I'm trying to write this a little more clearly. Mine was a little more. I don't waste time sometimes on the handwriting because I'm not interested in you just copying down. More interested in you just listening and then writing down what comes into your head for these. And then number 3, is the length of a shadow a function of the time? If so, is it linear? Well, if I want to know, well, first off, let's answer the first question. Does the length depend on the time? Does the length of the shadow depend on the time of day? So first off, yes, right? Does the length depend? The length, usually is a capital L, depend on the time. I always graph it. For every time, looks like at 0, for every time I'm getting one length. Now this line, and I'll prove it to you in just a second, is not necessarily straight. It's a little wiggly. Now I made it really wiggly. But nevertheless, I still get one time for every length. So if I look at this, if you remember, if I wanted to find whether or not something's linear, you're noticing, or if you haven't, if you notice, 10 is just about half of 20. So at 20 minutes, it was 10. You would think if I tripled 20, 20 times 3 would be 60. Well, 10 times 3, or 10 and a half times 3, should be 31.5, and it's 26. So it's not linear, meaning it's just not constant. There is no exact amount that the shadow is growing. And you might think, well, how is that possible? And for the sake of time, the sun is not necessarily what is moving kind of constant, but since it's at an angle, shadows aren't necessarily growing and or decreasing at a perfect rate. All right. 9.3, recycling. In an earlier lesson, we saw this graph. So we saw this graph not that long ago, and we described what it was doing at certain times of the years. And so now we're going to use the same graph again for a different activity. And it's going to take some concentration here in just a second, and you'll see why. In an earlier lesson, we saw this graph that showed the percentage of all garbage in the U.S. that was recycled between 1991 and 2013. Number one, sketch a linear function that models the change in the percentage of garbage that was recycled between 1991 and 1995. For which years is the model good at predicting the percentage of garbage that is produced? For which years is it not as good? So this might sound really confusing, but what it's actually asking, it says sketch a linear function that models the change in percentage of garbage. Sketch a linear. This is what we have to do in math sometimes. Read it over and over and over and break it apart till we can finally figure out what is it asking. Sketch a linear function. So what it's asking us to do is, it's a very complicated way of it saying, if it was really, really nice, but it wants us to understand the vocabulary, it would just say draw a line. Draw a line that models, and it has to be a line. It has to be a straight line. Linear means straight. So draw a straight line that models the change in percentage that was recycled between 1991 and 1995. For which years is the model good at predicting the percentage of garbage that is produced, and for which years it's not? So first off, we're going to focus. Here's 1991, and here's 1995. We're going to try to draw a single straight line that would represent all of these lines. So I could draw a line like this and pretend that's straight. That doesn't really represent those lines very well. So I don't want to draw that line. I could draw a line like this. Again, that doesn't quite, you'll notice that's not quite as steep as those lines are. This kind of line is a little too steep. And if I drew a line like this, that is just about as steep as that line's, but you'll notice those lines aren't anywhere near that line. So we do our best. I have this luxury, and actually I'll do what you have to do too, because I was going to say I have a line function, but I'm going to try to draw a line, and it doesn't necessarily mean that I just necessarily connect these two, but that is one solution, just connect and make a straight line. But you'll notice that only includes those two lines. These lines kind of get left out. We want to try to include, or not lines, those dots, those years. We want to try to include as many of these points as possible. We want them all to be kind of close. And there's no exact way. There actually is an algorithm on some computer programs that do this and do it relatively easily. And we can look into that. But as for now, I'm going to just kind of say, you know what? I think a good line would slightly miss that one. Slightly. And I'm making this as straight as possible. We're pretending this is straight. If it's not straight, then it's not linear. But notice I slightly missed that one. I'm still touching some of them. I missed that one. I missed that one altogether. But that's the best I can do. And now I can answer the next question. The part two, that's part one. And my line isn't, I'm looking at it, it's not as straight as it probably should be. Whoops, I'm erasing it now, that's not good. But it has to be exactly straight. So if we were to really do this, it would have to be that. If you were trying to do this, that would be wrong because it's not linear. Linear means we have to draw a straight line. And that means, as you can see, that, oh gosh darn it, why do I keep doing that? That means not all the lines get included. Or not all the dots, I'm sorry. That one is slightly off, and that one is slightly off. And even, well, either way, it's kind of just up to us to decide. But the next question says, what years was this model good at predicting the percentage of garbage? So we just made a model for 1991 and 95. For what years is this model good? Well, this year right there, looks pretty good. And, well, we could say 1991, 92, and 95 for that model. It was pretty good. We could argue that maybe those 2 points is not good. So we could say 91, 91, 92, 93, 94, 95. That's good. Smiley face. And we could say for 92 and 93, not so good. That's not a good model for those. And on the other, it's not a horrible model. It's not bad, but our line is a model. It's just giving us a rough estimate of what kind of increase we're seeing. And we'll practice this a little more tomorrow. What we're actually doing, this is called the piecewise function. We're just taking this piece by piece. We don't need to look at it all together. We can if we wanted to, but for right now, we're just looking at 1991 to 1995. And I continued my line through. Maybe I should have started it and stopped it right on 91 and 95, or right there, but I don't think it matters. But so we're kind of introduced to that, something new, something that you've never seen before, and we're gonna explore this again. So don't worry if this isn't 100% making the most of sense. At the very least, you should see, hey, you know what? I can draw a line that represents most of the dots. Question 2 says, pick another time period to model with a sketch of a linear function. For which years is this model good at predictions? So now you get to choose any other time period, and I'll leave it up to you. You can choose one. You can hit pause, and when you're, I'll let you do it. So you can pick a 5-year period. We just chose between here and here. So pick another 5-year period. If you chose between 95 and 2000, if you chose those, you're going to notice it's going to be tough to draw a line that represents those, but you can, and you'll just notice, some of them are going to be kind of right on that line and some of them aren't, and that's fine. That's the whole point of the activity. But go ahead and pick another 5-year period, and it doesn't have to be a 5-year. You could do a 4-year, but anything less than that, then you're kind of defeating the purpose. And then do exactly what we just did. With that being said, when you're done with that, go ahead and unpause the video. We're going to pause that and do that. But now we're going to look at Lesson 9 practice problems. The summary kind of is just explaining that, you know what? We've got linear functions, and sometimes they're just not straight, but there's still some data that we can get from it. So let's go on and look at the practice problem. It says on the first day after the new moon, 2% of the new moon surface is illuminated. On the second day, 6% is illuminated. Based on the information, predict the day on the moon's surface is 50%. And then 100%. So you can already see on the first day, it was 2, and then it went to 6 on the second day. So something doesn't seem like it's exact, right? Because it didn't go 2%, and then it didn't go 4% on the second day. So it's just one of those, again, where we can make some predictions, but might not be exact. But let's just go ahead and assume that on the first day it was 2%. On the second day it went 6%. So each day, let's just say that it's going up 4% every day. So when will be 50%? Well, if I keep going 4, 8, 12, 16, I'm seeing how many 4s. Or if I just did, 50 divided by 4. And how many 4s go into 50? I don't have a calculator, so we'll do it the old-fashioned way. So 12 and a half. So after 12 and a half days, maybe predict the day. So we'll say 12 and a half or 12 days. After 12 days, it would be, oh, whoops, it says and 100%. So if I did 100 divided by 4, well, that's just 25. So we would say 12 and 25 days. And then B says the moon's surface is 100% illuminated on day 14. Does this agree with the prediction we made? No, we said 25. And it doesn't say explain. That's nice of them. So all we have to do is say no. Is the percentage illumination of the moon's surface linear? A linear function of the day? Technically, this is not making a straight line. And we could see that right here at the very first day. If we went from 2 to 6, well, if it was linear, it would go from 2, 4, 6, 8. So it is not linear because it's not going to make a straight line. Because if it was, it would use our data, but it didn't. It used some different data that we didn't get. And it is true. Again, I think it kind of comes down to, I'm not 100% sure on the angles, but angles, different things don't necessarily line up perfectly perpendicular, so the shadows kind of grow accordingly. All right, number 2, in science class, Jada uses a graduated cylinder. We've done a problem like this, so this is one that you could pause and go ahead and do on your own. But in the meantime, I'll go ahead and do this, and when you're ready, you'll unpause it. Take a look at it, but it says in science class, Jada uses a graduated cylinder with water in it. Remember, a graduated cylinder is just something like that, right? And we're going to drop some marbles in here. She dropped 4 marbles in there. And so if you have a graduated cylinder, if the water level is here, when you drop marbles in there, right, the water level goes up. Let's use blue. Let's get all fancy. There's the water level. Now the water level is up there after we drop marbles, right? So after dropping 4 marbles, the water level was 10. After dropping 6 marbles, it's 11. Question 1, what's the volume of 1 marble? So this is marbles and this is volume. So when I went from 4 to 6, when I added 2 marbles made it go up 1 milliliter. So what's 1 marble? Well, 1 marble must be a half a milliliter. So what's the volume of a marble? A half a milliliter. If 2 is 1, well, then divide 1 milliliter among 2 marbles. That means each marble must be a half a milliliter. So with that being said, how much water is in the cylinder before any marbles were dropped in? Well, if 4 marbles made it 10, well, then I have to get rid of those 4 marbles. So if each marble is a half, 4 times a half is 2. So 4 marbles is 2 milliliters. And if it was 10 with 4 marbles, if I take out those 4 marbles, I do the 10 minus 2, and I would get 8. So what should the height of the water be after 13 marbles were dropped in? Well, now that we know we're starting with 8, I don't like how this works, but we'll go ahead and write it here. We're starting with 8 in there, plus the 13 marbles times a half for each marble. That's equal to 8 plus half of 13 is 6.5. So I believe we'd get what should the height be? The water in the cylinder is at a height of, it should be, it says height. It should say, what should the volume of the water be? That threw me off. I was like, how high will it be? Well, it would be a height of 14.5 milliliters, if that's such a thing. It's really just saying what will the volume of the water be. But maybe that's not exactly the volume. The height of the water will be at 14.5 milliliters. And then D, it says, is the volume of water a linear relationship with the number of marbles dropped in? Is it linear? If I were to graph this, would I get a straight line? Every marble, is it going to make the water go up the exact same amount? Yes, it will. Every marble is the exact same size. Every marble is making it go up exactly the same amount. If so, what does the slope of the line mean? Well, if you haven't guessed already, if you know what the slope is, doesn't mean necessarily starting at 0, since we are starting at 8, right? But every marble added is a half a milliliter. Guess what our slope is? It's a half. So what does the slope mean? Slope means it's the volume of a marble. The slope is 1/2. Every marble I add, it goes up 1/2. And I'm going to start at 8 milliliters. All right. It says solve each of these equations, explain or show your reasoning. So I'm going to go ahead and let's just say, let's get rid of that one. I'm going to do one of them for you, and I'll let you do the other one. I'll let you do the first one, and I'll do this one for you real fast. You can follow along with me. Maybe you can beat me. But step one is, when solving an equation, is get rid of parentheses. There is an easier and a faster way to do this. This is kind of saying 4 times this is equal to 8 times this. Believe it or not, I could divide this side by 4 and divide this side by 4. 4 divided by 4. If I have 4 of these, well, 1 2a plus 2 means I have just a 2a plus 2. 8 divided by 4 is 2, so I have 2 minus 3a's. Now, with that being said, I could do it the old-fashioned way. Maybe I didn't see that. Maybe I didn't see that shortcut. And I apologize. Some of you hate it when I do something and then erase it. But, well, that's just the way the cookie crumbles sometimes. I'll buy you an eraser tomorrow. 4 times 2a means I've got 8a. This is another way to do it. 4 times 2 is 8. 8 times 2 is 16. 8 times a negative 3a is a negative 24a. And now I can start solving this. Step 1, doesn't matter. I can do minus 8a, minus 8, minus 16, or plus 24a. I'm going to do plus 24a because I don't like dealing with negatives. That's going to give me 32a plus 8 equals 16. Those are gone. Next step is I've got numbers and letters on the left side, so let's get rid of the numbers. And now I have 32a, those are gone, equals 8. Next step is divide by 32, divide by 32, and guess what? A equals 8 over 32, and I'm done. I'm going to go ahead and simplify that. I do know that 832, if I divide that by 8, I do know that 8 goes into both of those, so I could get 1/4. But this is fine. That's even better. So go ahead and do that one. And when you're done, let's look at number 4. It says, for a certain city, the high temperatures in degrees Celsius are plotted against the number of days. So here are days, here is temperature. Based on this information, is the high temperature in the city a linear function of the number of days? Well, you would technically need a piece of paper or something that is straight to let you see. And luckily I have a function here. Let's see. And believe it or not, apparently, is the high temperature a linear function? Well, oops, go back to pen. Yes, they make a straight line. Linear, doesn't say explain, but it's straight. Now, that's probably not going to always be the case. It is here, but so be it. Based off of this, it is straight. We're done. The school designed their vegetable, number 5, their garden to have a perimeter of 32 feet. Perimeter, the distance, I like to draw pictures. Here's a garden, 32 feet. So the distance around that garden is 32 feet with a length measuring 2 feet more. The length is 2 feet more than twice the width. Twice the width plus 2. 2 feet more than twice the width. So this is also plus 2. And that's the length. I could call this the length, and this is the width and the width. You can interchange the length and the width. Some people call up and down the length. That's usually what I do. That's just what I wrote there. So, using L to represent the length of the garden and W to represent its width, write and solve a system of equations that describe this situation. So, what are the dimensions of the garden? I'm trying to think of a system of equations. Maybe it'll come to me, but right now it just means that I have this plus this plus this plus this. Add all those together. I guess what it's saying is it's saying 2 lengths plus 2 widths equals 32. It's saying 2 lengths plus 2 widths equals 32. And I'm replacing, I also am saying, well, this is saying, hey, length equals 2 widths plus 2 right here. So I guess now there's my system of equations. So if I drew that fancy sign, there's my system of equations. And every time I see a length now, every time I see that, I can replace it with this. 2 lengths, or length is 2 widths plus 2. So you're going to notice, you're going to see that here. Here's one of them. Here's the other one, which is why 2 of them is 2 times 2W, 2 W's plus 2. So, long story short, I've got, let's write it, let's just zoom in, squeeze it in here. I've got a W, got that one done, plus 2W plus 2, got that side done, plus another W, got that one done, plus a 2W plus 2, got that one done. And all of that is going to equal 32. So I solve all of that. I got a W plus 2W plus another W plus another 2W. That's 1, 2, 3, 4, 5, 6. That's 6 W's. And then I've got a 2 and a 4. 6 W's and 4 equals 32. So next step, maybe you guessed it, subtract 4. I got 6 W's equals 28. And therefore, divide each side by 6. W equals 28 over 6. We could leave it like that, but let's go ahead and 6 goes into that 4 times. That's 24 and 4/6 or 2/3. Phew, a lot going on there. Let's call it good. Let's call it a day. If you like this, hit that like and subscribe button. If you hate it, hit that like and subscribe button. If you kind of liked it, well, don't hit anything. That's it for now. Peace.